Hello, everyone. Welcome to our live session today. My name is Matthew, and I am one of the course instructors and developers for the classes on Coursera and Udemy. But there are probably many of you from the classes and from elsewhere, so we welcome you to this first live session of the new year. I'm going to hand this over to Professor Impey to welcome everyone, and then we will get started with questions.
Okay, welcome everyone. It's out in the real world, it's very tumultuous in the United States. We had our highest number of COVID deaths ever yesterday. The Senate is probably going to change hands. There are demonstrations in Washington the last flailing weeks of Trump's presidency. It's pretty crazy. So let's reassure and calm ourselves with the wide open spaces of astronomy. Floor is open for your questions.
All right, the first question we have is kind of a general question from World of Science, who is on with us live, who asks, astronomy as a whole is marked by a variety of uncertainties. So can you talk about what things are we certain of in astronomy? And can you talk about, sort of most interestingly, what are the uncertainties of things in the universe?
Right. So it's a good general question about astronomy and really about science and how it works. So first of all, astronomy is distinct from most science fields because it is the objects of our study are remote. So this is not a lab science like chemistry or biology, and it's not even a field science like geology where you deal with samples. Now we can't always inspect the interior of the Earth, so even geological samples are limited to the surface and near surface. But in astronomy, it's completely indirect. We have very few direct samples of the universe. We've visited a handful of objects in the solar system, only one in person and the rest by robotic probes. We have free samples of the solar system that land on Earth in the form of meteorites. And that's about it. Everything else in astronomy is learned by remote sensing using electromagnetic radiation. And in the last couple of years, gravitational waves, which is a completely distinct way of learning about the universe. So as such, we're limited by the data that we can acquire from deep space. And many of the objects of our study are very remote. Their light has traveled for billions of years through space and time, and the amount of light we gather is pitifully small sometimes from distant objects, even with large telescopes. So uncertainty astronomy is limited primarily by the remoteness and faintness of the objects under study, especially those outside the solar system and even more so outside the galaxy. So that's the first uncertainty. The data is limited, and we can't control the experiment because we're just remote sensing. A second level of uncertainty involves the nature of the objects we're studying. Because we deal with the radiation we gather from stars and galaxies and other parts of the universe, we have to infer the processes by which these objects work, stellar fusion or particle acceleration near a black hole or other physical mechanisms. We can recreate some of those mechanisms on the Earth in labs, but not all of them. So sometimes we're dealing with a theoretical uncertainty too, which is we don't know exactly how things work out in space, at the edge of a black hole or in these highly complex regions of magnetic fields and plasma at the center of galaxies. So that's another uncertainty. It ties into the issue of mechanisms and theories. There is an even more profound uncertainty that relates to our situation in space and time. We're bounded in what we can learn about the universe by the fact that light can only reach us that has traveled for 13.8 billion years, which is the age of the universe. So there could be regions of space that are beyond our view, essentially, and we don't know about them because there hasn't been time in the age of the universe for light to reach us from those regions. And so that's a profound uncertainty because that means essentially we're limited in our view of the universe. There's even a kind of uncertainty in cosmology that's called cosmic variance that relates to the fact that we may not be able to study large enough or fair enough samples of the universe, or to the fact that we only have one universe to study. So when we're measuring global parameters of our universe, we're dealing with a sample of one. So these are all examples of uncertainty that are quite particular to astronomy, and they really don't apply in other scientific fields.
Thank you very much. The next question is from Akshath, who is on with us live. I read that an asteroid as big or as large as the Eiffel Tower will hit the Earth. So first of all, is that true? And second of all, what fate lies for our planet if something like that were to happen?
Um, well, first, it isn't true. We do have, at the moment, as we speak, we have no definitive evidence that we're going to be hit by an object from deep space. Astronomers are tracking objects in deep space. Essentially, every deep sky object larger than about 250 meters in diameter is part of a catalog and is being routinely observed by telescopes around the Earth. And we monitor their trajectories and their orbits, and we would know if one was heading towards the Earth. Those are calculated and recalculated all the time. So none of those large objects is heading towards the Earth. Now, smaller objects, it's trickier because we don't have a complete inventory of things that are 50 or 100 or 150 meters across. We pick them up with our telescopes. We sometimes see that they're on an Earth approaching trajectory, and then astronomers make more careful observations, they do calculations, and they do predictions. And in every case so far, and in the cases that the question is alluding to, when those detailed calculations and better observations are done, it turns out that the object will not hit the Earth. Basically, the Earth is small and space is large. So the odds of any impact in that scenario are always very low. It will eventually happen. Obviously, the Earth has been hit by large pieces of space debris roughly every 50 to 100 million years. But on the timescale of human life, then we don't expect that to happen. So I don't think there's a prospect there. Now, an object the size of the Eiffel Tower, that's a few hundred meters in size, these are the ones that are cataloged by NASA and other observatories. And so we really do know those objects and where they are. So there is essentially zero chance in the foreseeable future for us to be hit by something the size of the Eiffel Tower.
Excellent, thank you very much. The next question is from one of our live participants who would like to know if you can talk about the existence of exotic matter or matter without mass in the universe.
There are various forms of exotic matter. That's a sort of catch-all term for various entities in the universe that are not the standard particle physics objects, which are leptons and quarks. There's light particles like electrons and neutrinos, and quarks that make up neutrons and protons, and then there are intermediate mass particles. So beyond that, there are other ideas. Obviously, there are supersymmetric particle theories that predict a shadow set of particles, which can have quite high mass if they're stable, that exist as part of a supersymmetric theory of particle physics. We have no evidence for their existence right now. Another form of unusual or exotic matter is called quark matter, that is hypothesized to exist in the centers of some very dense and very hot and high density cores of stars, where quarks essentially under very high pressure are actually able to be liberated in a way that they are not in a normal atomic nucleus. There's no direct evidence for quark matter either. There's indirect evidence that something interesting could be happening in the center of ultra-dense stars, but no one has seen quark matter directly, nor could we simulate it on the Earth. And there are various other forms of shadow matter, if you like, that come up every now and then in theories and speculation. But as far as observation of the universe, there's no evidence for any of these existing. Dark matter does seem to exist, and we believe it is a subatomic fundamental particle, as yet unmeasured in physics labs. But that's really the only form of what you might call exotic matter that astronomers are confident exists.
Excellent, thank you very much. The next question is from one of our live participants who would like to know if it's a very specific question, so we can address it and then maybe talk about sort of general possibilities. Cheeky Bear asks, if a hypervelocity star passed through a protoplanetary nebula, would it just absorb it, or would the nebula be ignited and form its own star?
So hypervelocity stars, first of all, what are they? They are stars that typically form in binary systems where interactions between the stars, or multiple star systems, where interactions between the stars in a multiple system can lead to a sort of slingshot mechanism where one member of the set of stars is given a very high kick velocity, enough to eject it from the system and potentially even from the galaxy. So some hypervelocity stars have been observed, and their radial velocities, their velocities are sufficient that they are not bound to the Milky Way. In a sense, they could leave the galaxy eventually. So these stars do exist. They're pretty rare, and we think we know how they're created. It's not a typical mechanism that happens very often. If such a star moving at very high speed were to move into a protoplanetary or protostellar nebula, it's not obvious what would happen. The star itself is quite small compared to the size of a nebula that will form a star. So it's possible, especially if it doesn't go through the heart of that nebula, that there's very little effect at all. It would just disturb the nebula, maybe wrench some of the gas from the nebula near the edges, and the nebula would settle back down to its normal state or configuration and continue unperturbed. It is possible, however, that a high-velocity star could create a shock wave at the outer edge of a nebula, and that shock wave of material might propagate far enough to create a collapse of that nebula and therefore trigger the formation of a star. So I think there are some scenarios where a hypervelocity star plowing into a protostellar nebula could trigger the formation of a star, but it's actually a low probability situation.
Excellent. Folks are just saying that your volume is a little quiet, so just make sure that you've got your microphone in a good place.
Good point.
And
it was on the desk. Okay, this should be better.
Okay, that should be better. Yeah, that's fantastic. All right, thank you very much. We have another question from one of our live viewers. We have 125 people joining us today, so thank you all for coming and talking about astronomy with us for this new year. We have addressed this question, I believe, before, so we can probably keep it a little short, but it's always interesting. Mohan would like to know, why is the sky dark at night when there are billions of stars all around us? Why isn't the sky colorful, or at least lighted up?
Right. The fundamental reason is that the density of stars in the universe, in the galaxy or beyond, is very low. Stars are physically small compared to the spaces between them. So most of space is empty, and as a corollary of that, most of space is also dark. In a cosmic sense, because most stars are in galaxies that are quite far away, another reason the sky is dark is because the age of the universe is not long enough for light to fill the entire voids of the universe, or the spaces between galaxies. So that's a second reason that the universe is quite dark. And a third reason is the expansion of the universe itself. The expansion of the universe creates a redshift, which reduces the energy and stretches the wavelength of distant light. And that reduction of energy of distant light is another way of saying it's sort of darkening the sky on average due to the expansion of the universe. And this, in the end, is the solution to the Olbers paradox, where in an infinite universe, you'd expect every sight line, every direction you look, to eventually hit the surface of a star or a galaxy, and therefore, logically, the entire sky should be bright. So though I've given the three reasons why we think the sky is not dark and why that's not a problem for astronomy, that's the case.
All right, Red Unleasher would like to know, what happens when a photon hits the mirror, like of a telescope, I assume they mean. What change occurs in the fundamental properties of the photon? I mean, is it somehow inverted, or does the spin change or something, or is it completely unaltered?
So when a photon hits a mirror, it's reflected. And so what does that mean? Well, you start by remembering that a photon is an electromagnetic wave. So in its essence, physically, a photon is a propagating set of electric and magnetic coupled oscillations moving at 300,000 kilometers per second through a vacuum, and they propagate through space. And how they behave when they interact with matter depends on the kind of matter. A glass is a dielectric, and so a glass surface, especially when coated with a metal, will essentially reflect the waves that are incident on them. And so these coupled electromagnetic oscillations essentially bounce, just in a mirror sense, off of that surface. Now, if there's no reflective surface, like the metallic surface of a primary mirror of a telescope, then the light will pass through the dielectric, through the glass material, And if it comes at an angle of incidence, it will be refracted through that material, and that's how you have the bending of light through a glass plane or prism. So what happens to light depends on what actual material it first hits, whether it is transmitted or absorbed or potentially reflected.
Thank you very much. Richard Tennis says is just feeling anxious in general and would like to know if you can talk about some interesting things to look forward to in 2021, either astronomical events or scientific achievements that we're expecting this year.
Well, in astronomy, I think there are some big missions that are on the horizon that are quite exciting. The big one for astronomers is the James Webb Space Telescope, this many-year delayed and many tens of billions of dollars over budget telescope, successor to the Hubble Space Telescope, is due to launch in October. It's a 6.5-meter telescope that will unfold in space because it's not being launched as a single mirror. It's a multiple mirror telescope. Very high degree of difficulty. It will sit at a Lagrange point, hundreds of thousands of kilometers from the Earth, in a place where it can't be serviced. And so this high-stakes project basically has to work, too big to fail. NASA has done a good job with it. It's passed most of its tests after some teething problems all around. And so people are confident it'll launch. The other area where there's a lot of activity is in the solar system. This is going to be the year of Mars. There is going to be the Perseverance Mars rover, which is a successor to the Curiosity rover that's on the planet now. So it's an upgraded version of that rover with life-detecting experiments. The Chinese are planning a Mars rover, and I think Saudi Arabia, the Arab countries in collaboration, are putting a rover on Mars. So Mars is going to get a lot of attention. I think there's, of course, still orbiters, and I think one more will be added to the mix this year. So Mars and JWST are the big astronomy stories and planetary science stories. In the rest of science, well, it's hard to tell. Astronomy is based on discovery, and so it's not really clear what the big discoveries of the future will be, because astronomy is driven by huge telescopes on the ground and in space, and discoveries are made pretty much all the time. I think it'll be a big year for astronomy, and undoubtedly a big year in other fields of science too. Remember that the progress in genetics and genomics and fields of molecular biology is extraordinarily rapid these days. These CRISPR techniques that we've seen for gene editing are moving at an incredible rate. So if you're talking about overall in science, that's clearly another area where there's going to be dramatic progress this coming year.
Ashley Anderson sent an email. It's a very, very profound philosophical question. Why is it important to explain the universe in terms of mathematics? Humans don't, sort of speak in terms of mathematics, and we don't exist in mathematical form. Do you think it would possibly be more beneficial to explain the universe in terms of purpose and value?
That's an interesting question. The first part of the question explores the point about mathematics, the role of mathematics in modern science. Physical theory especially is grounded on mathematics. So all our fundamental theories of nature, of matter and radiation, are based on mathematics, often very beautiful mathematics. That includes general relativity, the theory of gravity, the quantum theory of subatomic phenomena, electromagnetic theory that explains light. All of these theories have a mathematical form, and that's how they're expressed. These successes over a couple of centuries now, since, for example, electromagnetic theory at the time of Maxwell in the 1870s, have given cosmologists, physicists, and astronomers a lot of confidence that the fundamental theories of the universe that explain a lot of what we see have a mathematical basis. That isn't to say they have to, or that there are theories that might be non-mathematical that are relevant, but mathematics does seem to underlie our most successful theories, and so physics and astronomy work together in this regard. And that distinguishes astronomy, of course, from other fields like biology or geology, where you're dealing with composites of fundamental objects and particles, and the mathematics is now a much more complex form of mathematics to describe sort of composite and complex phenomena. So, mathematics seems to lie at the heart of physical theory based on a century of research in particular. Does that rule out theories or ideas that are based on values? Not directly, but it does mean that the strength of science is in explanations which can be rooted in a physical theory that makes predictions that can then be tested. That's how the science advances. A theory based on values or morals or ethical considerations certainly could have value, but it involves a different type of scholarship. It involves a different type of logic, a different type of thought. It's not that it's invalid, it's actually much harder to execute, because in the end we're not sure whether our moral frameworks or ethical principles or value systems are universal or just a human construct. We do believe, in fact, that mathematics is universal. And that's why when we make our primitive attempts to communicate with extraterrestrial civilizations, we often use mathematical coding of a message because we think it will have universal value or universal meaning.
All right, the next question from email is whether we want to learn how to make 600, oh no, never mind, that's from the Nigerian prince. Sorry, the next one is from Prasanna Ravi, who asks about the Great Conjunction, which happened on the 21st of December, that was visible in the sky. Can you explain how it was visible? Is it due to the reflection of the light of the sun, or is it from something else? How is that visible?
Yes, the conjunction that we were talking about that many people were treated to in the days before Christmas is a phenomenon that occurs not regularly, but very occasionally. This was as good a conjunction as we'd seen for 600 years since the Middle Ages, and the next good one will be after most people living now are dead. So this is a pretty rare event. It just corresponds to a juxtaposition of two planets in the same sightline that have very different orbital periods. So it's just unusual and takes a long time for them to nearly line up. The phenomenon we're seeing, of course, is reflected light from the sun. So planets do not shine by their own light. They shine by reflected light from the sun. And so we essentially are relying on the sun's energy going out a distance of 1 billion or more miles to Jupiter and Saturn, and then coming back that same distance or a bit more to the Earth, and for us to see them. So that's why these objects are faint, because they rely on reflected light and that there are large distances. But that's true whether they're in conjunction or not. These planets are always shining by reflected light. And how bright they appear in the sky simply depends on their distance relative to the Earth and the sun, the source of the light we see.
Excellent, thank you very much. The next question is from one of our live participants who would like to know, so Mango Jones asks, how and why is it that the solar system planets are configured the way that they are?
Well, we think it was mostly due to initial conditions. So the solar nebula, the enormous gas and dust cloud that eventually formed the sun and the planets, was slowly rotating and eventually collapsed by gravity to form a disk. And in that collapse, the polar axis collapses more quickly than the equatorial axis, which is sustained by the rotation and the angular momentum of the material in the disk. And so you end up with a disk-like formation system, which then aggregates within the disk, nucleates into planets which accrete their material to form solid cores and gaseous envelopes. And that's, in very rough terms, how you get a solar system. So the fact that the planets are all roughly in a plane, seen in the sky as the ecliptic, the path of the sun, they're all quite close to that, and the fact that they all move around the sun in the same direction is a reflection of initial conditions and the angular momentum of the nebula that formed them. The more detailed behaviors, like how much these planets deviate from the ecliptic, because they all have slight tilt angles, ranging from a couple of degrees up to a large number of degrees for outer planets, and the tilt of their spin axis relative to the equatorial plane, which also ranges from only a few degrees for the giant gas planets to 25 or so degrees for the Earth and the Mars. So these details we think are also connected with initial conditions, but something else is required to explain those particular properties. So the solar system is a combination of initial conditions which give the large-scale properties of the solar system and its systematic motions, and then more detailed things that happen later on, which lead to, for example, things like the formation of our large moon of the Earth, the tilt of the various planets' spin axes relative to the equatorial plane, and, for example, the fact that Venus is counter-rotating, so it goes against this trend, and Uranus is almost tilted on its side in terms of its spin axis.
The next question is from Hernan Reyes, who is on with us live and sent an email. Their question is about Europa. You've commented before how tidal heating keeps the water in the underwater ocean in liquid form. Could you please explain whether the orbital resonance of the 3 Galilean moons combines with the massive gravitational pull of Jupiter itself to generate this tidal heat? Does the resonance have anything to do with it, or is it simple, simply something else?
No, the resonance is actually an important component. I don't remember the relative proportions, but it's substantial. So the resonance heating from the moons, their fact that their orbital periods are ratios of whole numbers, which is what creates a resonance situation, that's a significant component of the heating. The other component is tidal heating caused by the eccentricity or non-circularity of the Europan orbit. If Europa was in a perfectly circular orbit of Jupiter, its tidal heating would not change. The tidal force on the moon would be the same anywhere in its orbit. It's because it's in an elliptical orbit that the tidal heating changes through its orbit, and that creates a heating effect. And then the final component is, of course, also significant. I don't remember the exact fraction, but the simple geological heating, the fact that Europa is a substantial moon with a rocky mass. That rocky material has radioactive elements in it. Those radioactive elements create heat through radioactive decay, which percolates up through the rock and provides a mild heating to the base of the European ocean. So it's a combination of those 3 things, and they may actually be roughly similar in importance.
Thank you very much. The next question is from Francine Kaplan, who's on with us live. When you talk about forces in the universe and matter, are there predictions of what the initial force was that created the Big Bang?
Not really predictions. There is an expectation that at the point of the Big Bang, which is a singularity, which is essentially a non-physical situation that we don't understand, of essentially infinite temperature and density, that the 4 forces of nature were combined or unified. We have good evidence from physics that at sufficiently high temperature, forces that might be distinct at lower temperatures take equal strength. We've proven this with 2 of the 3 forces of nature at CERN in the 1970s, and we have somewhat indirect evidence that 3 of the 4 forces of nature merge at a very high temperature beyond available to accelerators now. The temperature required to create unification of all 4 forces into an uber force, an Ur force, is phenomenal and far beyond our capabilities. So it's very much a speculation that there is a theory of everything, if you like, a super force that constitutes the merger of general relativity and quantum mechanics. That's a theory we don't have right now, which is why we can't really fully understand it. So it's very much speculation based on the initial condition of the universe with no real good predictive theory to plug into this situation. So we're pretty much in the dark about the early Big Bang.
Excellent, thank you very much. There's a follow-up question, kind of a related question to the earlier Europa question. Hernan would like to know, Enceladus has great fissures in its southern hemisphere, the tiger stripes. How is it that these cracks don't freeze in between geyser activity? What keeps them open in such an intense, cold environment?
That isn't really clear because we haven't got very good observations of this. However, if the icy geysers are produced in the subsurface, in a subsurface ocean of Enceladus, then the heating again will be episodic because of tidal forces. So Enceladus, which doesn't have enough rocky mass to create heat by radioactive decay, is really subject to a tidal force from Saturn, and that's what gives it its heating. So that tidal force and heating will essentially impel these water jets up through the rock, and as soon as they can escape from the planet's weak atmosphere, they of course turn into tiny ice particles as they hit the incredible cold of deep space. So the fissures in Enceladus are not always leaking material into space. It will take some activity in the deep surface ocean to force liquid water through fissures in the rock, and at the point where it gets to near the surface, then it will escape as an icy jet. So there's a process of essentially extruding these jets out into space by the force of heating from inside.
So there was kind of a news blurb a few weeks ago about a possible radio signal from the direction of Alpha Centauri, apparently. And Scott Childs would like to know how long ago something like that would have been sent, if it was sent from Alpha Centauri.
Right, it's from Proxima Centauri, they think, which is just a little over 4 light years away. So that's the travel time of a radio signal is just over 4 years. So that signal was not sent long ago, if it is a signal. However, what I would say is there's been a lot of discussion about this signal's RC1 event, is what it's often called. And astronomers have been, unfortunately, the information about the event was leaked by someone on the science team, because normally the protocols of these SETI experiments are that they pretty much keep it close to their chest until they've really confirmed that it was not an artifact or a contamination or just something terrestrial. Now, this signal did pass 3 or 4 internal tests that would have filtered out noise or some glitch in the instrument or some glitch in the detector. And it definitely passed those tests, and those tests were also designed to filter out terrestrial sources of radio noise or radio signals. It passed all those tests, but that does not therefore follow that it's an extraterrestrial signal or an alien artificial signal. And I think unfortunately, when that signal was leaked, or when the information about that signal was leaked, the scientists hadn't had their full chance to explore what might be going on. And most of the scientists involved, and now they've started to speak and write for the media, are still being extremely cautious. They're saying, by no means have we ruled out all natural causes for this signal, this radio signal. We're not jumping to the alien communication hypothesis yet. I think once it got out into the media, speculation took over. Other scientists who weren't as close to the project were commenting and maybe being a little, maybe slightly frivolous in their ability to latch on to the alien communication hypothesis. But the team involved, who actually know the data best, are being extremely cautious, and none of them are saying, "We found ET."
Lawrence K. has a hypothetical question. If we were to shine a beam of light into a perfectly square box of mirrors so that the light is reflected and not absorbed, so essentially it's not absorbed by the box, but it is still contained within the box sort of permanently, would the mass of the box increase?
That's a good question. Mass, photons do have an equivalent mass, of course, by E equals mc squared. So yes, in principle, if light could be captured or contained in some structure, that light has energy, and therefore it has a tiny amount of equivalent mass. But it's a really tiny amount of equivalent mass. It's quite possible that it's an unmeasurably small amount of mass in any experiment to measure the change in mass of that instrument. So while hypothetically, yes, that is true, I think as a practical matter, this is not an experiment we can actually do to measure the gain in mass of a photon trapped in an object.
Another hypothetical, and I'm not sure why we would do this, but Sudhanva, who's on with us live, would like to know if we could oxygen bomb Jupiter. So, how much oxygen does the atmosphere of Jupiter have, and what would happen if we added tons and tons of oxygen to its atmosphere?
Yeah, I mean, Jupiter's atmosphere composition is pretty well known. It's overwhelmingly hydrogen and helium. There's moderate amounts of methane, and then some actually quite toxic gases, like even acetylene is included there. and hydrogen cyanide for very small trace amounts. Oxygen is a negligible component of the Jovian atmosphere. So if we did an experiment where we just sent compressed liquefied oxygen and then dumped oxygen into down into the Jovian atmosphere, what effect would it make? Well, we don't have the technology or the capability to put enough oxygen into Jupiter's atmosphere to make an even measurable effect on its composition. Now that gas, because it's substantially heavier, more massive molecule than hydrogen and helium, would sink quickly to the base of the Jovian atmosphere. The base of the Jovian atmosphere is actually a situation of very high pressure and temperature. And so at some point that oxygen would be pressurized and liquefied, by being under intense pressure, basically, because there's even liquid hydrogen and metallic hydrogen, we think, at the base of the Jovian atmosphere. So that's probably what would happen to that oxygen. It would not oxygenate the atmosphere of Jupiter and make it potentially breathable, for example, in any future scenario. It would fall straight towards the center of the planet and its rocky surface and turn into a liquid film around that core.
Thank you very much. The next question is from Red Unleasher, who's on with us live. Apparently, we just found the oldest galaxy in the universe. Can you talk about this discovery, like the redshift, dark matter and energy that exist there?
Yeah, there's been a few papers in the last year on distant galaxies. The one that you're talking about is claimed to be the most distant galaxy in the universe. It's claimed to have an age of about, I think it's about 13.1 or 2 billion light years. So it's within 500 million years of the Big Bang, which is very early in the universe, in the first 5% or a few percent of the universe's age. It was found with the benefit of gravitational lensing, giving a boost to the signal, which is often how we see galaxies that are that far away. It also seems to be a rather massive and mature galaxy, and that's been interesting to the people who discovered it, because the standard theory of galaxy evolution and formation is that small galaxies form first and merge hierarchically into forming bigger galaxies like the giant ellipticals in our nearby universe. So this is an unusually massive galaxy, unusually early in the universe for that to be found, and nobody really knows whether that's a problem for the model we have of how galaxies form and evolve, because of course the only galaxy you could see that far away is a massive galaxy. The normal sized or small ones you don't have the sensitivity to see, so there could be lots of those. So we're going to pick off the top of the deck, if you like, of the most massive galaxy. It's not clear you can draw too many conclusions based on one, but it's a very interesting object, and it was a technical tour de force, not only to detect it with imaging, but also to show its redshift, which required spectroscopy. And that's really challenging, because at that redshift, the visible light from the galaxy is shifted almost to the infrared, so you actually need near-infrared techniques.
The next question is from Simon Wells, who's on with us live, who would like to know, does dark matter really exist?
We think dark matter exists because we see evidence that the universe has decelerated in the past, before it started accelerating in the last 5 billion years. We see evidence that galaxies have some structural integrity and are bound, even though the number of visible stars in the galaxies is insufficient for them to be bound. They would not be contained. They would be evaporating or spreading out in space or disappearing over time. So all of these things indicate there's something out there like dark matter. And perhaps the best evidence of all is that the gravitational lensing. Because in gravitational lensing, mass bends light, and it doesn't matter whether mass is visible or invisible. It bends the light, and we can explain that bending by general relativity. And so in these lensing experiments, it's very clear that there's dark stuff that has mass and exerts gravity that is causing lensing, and so we can measure how much of that there is. And all of these methods converge on about 6 times more dark stuff than visible stuff. So especially because of the lensing type of data, astronomers are pretty confident that dark matter does exist. It is real.
The next question is from Arav Gupta, who's on with us live. Do you think that our universe could have started from a black hole or a wormhole from another universe?
That's an interesting speculation. Formally, I suppose you would have to say that the Big Bang at some level does meet the definition of a black hole because it's, for example, a singularity, and that's infinite cusp of density and temperature, and definitely fits the qualification or meets the qualification of a black hole with an event horizon and so on, and a singularity at the center. So in some very not direct analogous way, you can think of the Big Bang as analogous to a black hole. But in general, we don't really understand the Big Bang. So I think physical theories about the Big Bang like that, or even analogies with everyday objects in our present-day universe are a little premature. We need to know a lot more about these physical conditions, which means we need better theories of nature, actually.
The next question is from MKR, who is on with us live, who would like to know simply, why is it that planets have gravity?
Planets have gravity because anything with mass has gravity. Hard as it is to believe, even electrons have gravity. When electrons interact with normal matter or each other, the electrical force is so much stronger than gravitational force, many, many orders of magnitude, that we just simply forget the fact that they have gravity. But they have mass too, and so they act and interact with each other by gravity, if we could measure it. Everything that we know of in the universe, large or small, when we can create the correct circumstance or experiment, manifests mass, manifests gravity, and the gravity behaves as we would expect from our Newtonian theory and our Einstein theory. So we have a lot of confidence that everything out there has mass and that it exerts gravity.
The next question is from an email from Aisha, who would like to know, I guess she was listening to Neil deGrasse Tyson's podcast, and they were hypothesizing the discovery of a graviton, which led Neil to say, if we have gravitons, then gravity, being the curvature of space and time, has no meaning in the presence of a graviton. Could you talk about what this means and how that could, how the existence of a graviton would affect what we know about gravity?
Yeah, so Tyson is right that there's a conceptual difference that's in place here. It's two different ways of thinking of physical theory. The idea of a graviton is really rooted in sort of conventional standard particle physics, which goes back, basically a century, where every particle, every force has a particle that carries that force. The electromagnetic force is carried by photons, for example, and in this framework, the gravitational force is carried by gravitons. In the standard model of particle physics, a graviton is a spin 2 particle. It travels at the speed of light, so gravity would propagate at the speed of light, so we'd need to, for example, test that to even know if the graviton idea worked. And with gravity transmitted by a particle, it does deviate substantially from the conceptual view of Einstein, where gravity is essentially an effect of curved space-time. So mass and energy together create the curvature of space and time, which is hyphenated or connected entity. And that, therefore, leads to the trajectories of objects moving through that space and time. And that's a very different concept from the graviton idea. The graviton idea is more almost like a Newtonian idea in terms of how a force propagates. The jury is out on gravitons. No one's ever detected a graviton, nor even confirmed directly that gravity propagates at the speed of light, as it might do if it was carried by a particle. So I think the graviton idea is just that. It's an idea at the moment with no experimental verification.
William Warren, who is on with us live, would like to know, since it takes light from the stars, very distant ones, so long to reach us, how do we know that the stars are still there?
We don't. And in fact, depending on the type of stars we're measuring, we could easily infer that they're not still there. So for example, if we don't even have to talk about the very distant universe for this. I mean, suppose we measure a supernova or a dying star or a massive star late in its life in a galaxy that's 100 million light years away. which is not hard to do. So like a red supergiant or a blue supergiant in a galaxy 100 million light years away, somewhat further than the Virgo and Coma clusters. We could say, based on the spectra of that star and our measurement of it, that we think this star is massive enough and late enough in its life that it only has a lifetime available to it as a main sequence star before it dies as a supernova of maybe 10 or 15 million years, or maybe only a few million years. And yet the light took maybe 100 million years to get to us. So as we speak, we can say that, well, yes, we're looking at 100 million year old information, and that star in fact died, 98 million years ago if it only lived another million or 2 years. So it's absolutely the case that for some objects in space where their lifetimes are modest, they might not exist at the now of the time we receive the information, given how long it took for the information to reach us.
Excellent. A question that I forgot to include from our previous participant, Aisha, was asking if you host a podcast and would like to know if you'd be willing to do that. If not, I urge and request and encourage you.
It's a good idea. I've had it on my agenda. I think I did a podcast briefly once 10 years ago. It's hard to keep up the cadence of these things, because to do a podcast well, and we do have the technical capabilities and resources to do that, you pretty much have to do it regularly. You have to keep it up and do it routinely. It's not a problem of the lack of things to say or content, or even the ability to make a podcast. It's sort of the fact that there's a lot of stuff going on. As Matthew and I well know, we're in the business of writing proposals and grants and papers, and just the research of our group takes a lot of time, and we like to support the MOOC with these live sessions, and we're building a new MOOC right now, so it's sort of just a little too much for me to put on my plate right now, but I take the encouragement, and it's something I might well consider this year.
Yeah, and something we've done in the past is we've taken these live sessions and tried to turn them into a podcast that can be downloaded. I don't know if people would be interested in that when they can just listen to them live here on YouTube, but that's something that would be interesting to find out if people would listen to. The next question is from Eugene, who would like to know, where does the idea of the multiple universes come from? Does it have any scientific foundation?
Well, the original multiverse idea actually goes back to the 1930s, and a man called Hugh Everett, a famous physicist, and he came up with what's called the many worlds interpretation of quantum mechanics. And this was an idea that, as a way of understanding the probabilities that apply in quantum theory between different outcomes, he instead speculated that all the outcomes actually happen in a sense of branching. So universe at every point in every physical process branches out into all the possibilities that are laid out by quantum theory, and that they all each actually happen in a different parallel universe. And so as you can see, you quickly propagate up to this almost infinite amount of branching, exfoliating universes from a single origin. It's a very conceptual, almost a purely philosophical idea, the many worlds theory, but it's essentially the basis for later speculation on the multiverse itself. So there's an idea in physics that's analogous to multiverse. The modern multiverse idea in cosmology really stems from the idea of inflation. If inflation is correct as an early stage of exponential expansion of the infinite universe, then the universe was originally a quantum event. And if the universe was a quantum event, quantum events are governed by randomness, and quantum behaviors from one system to another are randomly different, it's possible to imagine a precursor state to the Big Bang, which could have led to other quantum events turning into other universes, or not turning into any universe at all, being stillborn, and that is now the modern basis for the multiverse. So it's based on the universe as a quantum entity and the idea of inflation, which has some evidence to support it. The multiverse, however, does not have any direct evidence to support it, because to believe that idea is correct, you would have to somehow have evidence of these distinct spacetimes. And since they are distinct, that logically is a difficult issue, a difficult problem.
The next question is from Divya, who would like to know, why do solar flares impact electricity? I assume they mean by like blowing out electrical grids.
Mm-hmm. Right. So solar flares are prominences that come off the sun, and you can see from satellites like SOHO and the modern version of the solar probes that NASA has launched, these spectacular prominences that loop plasma, high-energy particles, hundreds of thousands or millions of miles above the sun's atmosphere. When that energy leaves the sun, it travels through deep space. Not always quite at the speed of light, because these are high-energy particles, not photons necessarily. And when those high-energy particles, accelerated essentially by the sun's magnetic energy indirectly, when they reach the Earth, they interact with the Earth's magnetic field, and so they are going to dump a lot of energy down through the Earth's magnetic field down towards the surface. It's electromagnetic energy, and it can be in the form of a pulse. And so this kind of phenomena can be very hazardous to the power grid, because the power grid is a high voltage conversion system which is generating electricity at very high voltage, down selecting it for transmission through power lines, and then down selecting it further to put into people's homes and factories. And these external facilities, because they're out there in the open, are indeed susceptible to high energy radiation coming from space. And solar radiation during a flare is extremely strong. And so there is very good evidence that in 1965, when there was a large flare, not quite a super flare, but a very strong solar flare, a large part of the North American grid on the northeast, extending into Canada, was taken out for some period of time. And that's not the strongest solar flare we could have. If we really did get a super flare, even with our modern electrical grid, that's improved somewhat since 1965, it's not robust enough or resilient enough to survive a full-on solar storm from a super flare. This is a concern. This is a concern that astronomers have raised, and national security experts and people in telecommunications and power systems are fully aware of, and they're trying slowly and steadily to immunize our grids and our electrical capabilities from such an event.
Kind of a follow-up is, when we see northern lights, is that caused because of a solar flare?
The northern lights is a gentler phenomena, because the solar lights, the northern lights, aurora borealis and australis in the south, don't wait for solar events or have any dependence strongly on the solar cycle. You can see the aurora most times of the year and throughout the solar cycle, but it is stronger when solar activity is higher. So this is a more routine interaction of the solar wind with the magnetic field of the Earth. And it just happens that when the Earth, if you're near the magnetic poles where the field lines are converging to the surface of the Earth, that facilitates the passage of this radiation and these particles down those field lines, where they spiral along the field lines because they're charged particles emitting a lot of radiation. So you're preferentially going to get a lot of this energy deposited and a lot of the luminous emission from these high energy particles near the magnetic poles. And that's why the aurora is a phenomenon of the polar regions. It's north and south.
The next question is from Samarth, who would like to know, since the sun is in space, why isn't space hot?
Well, space is actually hot. Space, in deep space, far from stars or galaxies, is very cold. It's 3 degrees Kelvin, 2.7 Kelvin, which is the temperature of the microwave radiation left over from the Big Bang. So most of the universe, space, is very cold, that cold. Near the sun, space is actually quite hot, even though it's a vacuum. The solar corona, which is a region just beyond the edge of the edge of the sun that we see a surface, which is the photosphere, and then beyond that is the chromosphere. The corona of the sun has an equivalent temperature of 1 or 2 million degrees Kelvin, even though it's extremely diffuse medium. The amount of energy that's deposited in there, sort of magnetic energy essentially, dumped via high energy particles into the corona, creates an enormous equivalent temperature. And so it is a very hot region. Much hotter, as you can tell, millions of degrees is much hotter than the thousands of degrees that the surface of the sun is. So some parts of the space near the sun are actually extremely hot.
The next question is from David Gold, who would like to know, how important is Jupiter in protecting the Earth from destruction?
Yes, Jupiter has been called by some planetary astronomers our sort of guardian planet. It does have an interesting role in the solar system. And now that we've found other solar systems with different configurations and geometries, and solar systems that may or may not have a giant planet where Jupiter is in our solar system, we can now see just how somewhat unusual and special the position of Jupiter is with respect to the terrestrial planets. Essentially, Jupiter acts in a way where if there were an influx of material from the outer solar system, say passage of a nearby star triggers the Oort cloud or the comet cloud to convulse and sends a set of Earth-moving objects towards the inner solar system, then Jupiter has such strong gravity and such a large reach of its gravity that it manages to deflect and even eject many of these incoming objects from the inner solar system. And so it does act in an indirect way to protect the Earth from these fluxes of invading particles or objects. So we've seen that phenomena, and if Jupiter didn't exist, and that protection wasn't there, it's possible that Earth may have suffered many more catastrophic impacts than it has in 4.5 billion years.
Excellent, thank you very much. Atsan would like to know how we can use the Doppler effect to deduce how astronomical objects are moving through space.
So the Doppler effect is familiar. Christian Doppler was a German physicist in the mid-19th century, and he was doing experiments with sound waves. And so when a source of waves, in this case compression waves in air, that's what sound waves are, when a source of waves is moving with respect to the surrounding medium, it compresses the waves in the direction of its motion, giving them a shorter wavelength, higher frequency, higher energy. And in the direction away from the motion, they stretch out and so have longer wavelength, lower energy, lower frequency. And the same thing happens with electromagnetic waves. And so when we think an object is moving through space and it's emitting light, then we would expect that light frequency or wavelength is modulated by its motion. And essentially the Doppler effect is the ratio of the object's motion to the speed of light. The speed of light is a very large number, so this Doppler shift for light, for stars, say, is a pretty small amount. 30 kilometers a second is a typical speed of a star relative to another star or objects within our solar system before they escape. 30 kilometers per second is a large speed, but the speed of light is 300,000 kilometers per second. And so you can see that the Doppler shift of a typical object moving at the speed of a typical star in our part of the galaxy is 1,000th of the speed of light, and so the Doppler shift, red or blue, is just 1.1%, so it's a pretty subtle effect. But we have high-resolution spectrographs that make that actually fairly easy to measure.
Thank you very much. The next question is from one of our online participants who's on with us right now. They would like to know more about light. Do different frequencies of light bend in their own force or angle?
Yes, the effect of a prism, the phenomenon of a prism is perhaps the easiest way to see this. When light is incident at an angle in a prism, then the angle of refraction, or the speed of the light in that medium, depends on its wavelength or frequency, and that's what leads a light to disperse in a prism, and you get the colors of the rainbow out at the end. So it is true that the propagation speed of light in a medium, a transmissive medium, which could be liquid, gas, or solid, does depend on frequency, and that leads to dispersion of that light.
Andrew Johnson would like to know, what would an observer see at a place where frame dragging occurs, as opposed to a place where general relativity might be ignored?
Well, frame dragging will happen, of course, when the gravitational field or force is fairly strong. Now, frame dragging doesn't have to have extreme gravity situations like neutron stars or black holes. The frame dragging effect was seen in the 1980s and then published in the 1990s by Gravity Probe B. So Gravity Probe B was a satellite mission launched by NASA that was designed to test general relativity. And it was essentially looking at the Earth's gravitational field and the Earth's alteration of space and time in two different ways. It was looking for the actual bending of space-time by the Earth, and it was looking for the effect that would have on a gyroscopes, very accurate gyroscopes on the satellite. But it was also looking at the frame dragging effect, which is caused by the Earth's spinning while it deflects space-time. And that leads to a sort of a swirling motion, if you like, of the space-time contours, and that's the frame dragging effect. Gravity Probe B measured both effects. It measured the basic distortion of space, and it measured the frame dragging effect. Not extremely accurately, but it measured it. So we know this effect is real. That was a good confirmation of general relativity, and that was in a situation of pretty mild gravity, because the Earth is not a very massive object. It's much harder to arrange a neat astrophysical experiment to measure frame dragging in a black hole, around a black hole or a neutron star, although people are trying to attempt that experiment.
All right, it's now 2:05 here in Arizona. We are going to wrap up. I think this will be our last question that we have time for today. And we will take the question that asks, how come our solar system formed so seemingly perfectly with our planet Earth spinning around exactly the same way in a place where life could exist, and all those, the planets in our solar system seemingly perfectly aligned?
So the regularity of our solar system is really down to physics and initial conditions. It's down to the fact that the behavior of the solar nebula, once it's collapsed to form objects, was dictated by conservation of angular momentum. So the spinning gas cloud, when it was very large and nebulous, had a certain amount of angular momentum. And as parts of that gas cloud collapsed into discrete objects, angular momentum was conserved, a standard physics principle. And so the angular momentum of the initial system is reflected in the angular momentum of the objects that form. That angular momentum is boosted because the cloud collapsed, and so its radius or size decreased, which meant that the angular momentum of pieces of it would increase. So the sort of perfection or symmetry or regularity of the solar system is completely due to simple physical principles of conservation of angular momentum and also conformation of energy. Now, it's not particularly simple because the planets all have their slight irregularities, but the overall regularity is well explained. Now, this scenario, of course, doesn't explain the particular properties of the Earth and why the Earth should be the only planet in what we might call the habitable zone of our star. But in the end, given the large number of ways that planets can form around stars, that's sort of just a coincidence. Some Earth-like planets will form at a distance where they can be habitable, and some will form at distances where they are not habitable. And we've seen both examples elsewhere in the galaxy. Thanks very much for all your questions. Good questions and varied as always. And we already have a scheduled session for next week, which it's been announced. So I hope to see you all next week. And thanks for facilitation by Matthew and Alexander behind the scenes. Goodbye, everyone.